Hi, I'm Xifan Yu. Thanks for coming to my talk. Today I will talk about our paper, Statistical Inference of a Ranked Community in a Directed Graph. This is joint work with Tim Kunisky, Dan Spielman, and Alex Wein. In this talk, we only consider directed graphs in which there is at most one directed edge between every pair of vertices. And for this kind of directed graph, we could represent them with a skew-symmetric 0 plus minus 1 matrix. Below is an example where on the left we have a directed graph on 4 vertices, and on the right we have a 4x4 skew-symmetric matrix representing it, with Gij being +1 whenever there is an edge from I to j, -1 whenever there is an edge in the reverse direction, and 0 whenever there is no direct edge between I and j. We consider the following two models of random directed graphs. In the null model Q, we have DMP, where between every pair of vertices, we have a directed edge with probability P, and it has the same probability pointing in one of the two directions. And with probability 1 minus P, there is no directed edge between I and J. In the Ponted model, there is a hidden community structure with the hidden community S of size K that is Q correlated with some latent permutation ranking, permutation/ranking, and has the same edge density P. To be more precise, in this model, between every pair of vertices within S, suppose I counts before J in the latent ranking, we generate a directed edge from I to J with probability P times 1/2 plus Q, and a directed edge from J to I with probability P times 1/2 minus Q. And we do not generate directed edge between I and J with probability 1 minus P. And between the rest pair of vertices, we generate directed edges according to the null model. In other words, between every pair of vertices, there is a probability P for the existence of a directed edge. But for pairs of vertices within the hidden community S, this directed edge is more likely to point in the direction given by the latent ranking. In particular, if Q is equal to 0, we get back the null model. Whereas if Q is equal to 1/2, whenever there's a directed edge between I and J, the directed edge points from I to J if I comes before J in the ranking. We consider the following two fundamental problems for these random models of random directed graph. We first consider the detection problem, where we want to distinguish whether a given directed graph G is generated from the null model or the Ponted model. We also consider the recovery problem, where given a directed graph G generated from the Ponted model, we want to recover the hidden community S and the latent ranking pi. The parameters we consider in our work include the following. We first consider the log density setting, in which case the parameters Q, K, P scale as polynomials in N for fixed numbers alpha, beta, and gamma. We also consider the Ponted total ordering in a tournament, where the hidden community is counted on the whole set, that is K is equal to N and P is equal to 1, meaning that we observe a tournament. And we consider the situation of a Ponted ordered clique in a tournament, where P is equal to 1, meaning that we observe a tournament, and Q is equal to 1/2, meaning that whenever we have two vertices within the Ponted community, the directed edge between them is gonna point in the direction given by the latent ranking, and that the sub-tournament induced on the Ponted on this Ponted community is acyclic. We know that our models of random directed graphs are natural, and a number of related models has been well studied in the literature, including noisy sorting, BTL model, and the Ponted dense subgraph Ponted clique model. One of our main results in the work is that we determine the threshold for we determine the statistical threshold and computational threshold for detection and recovery in the log density setting. The thresholds here are written in terms of alpha and gamma. Whenever beta is above the threshold, the relevant task is possible, whereas whenever beta is below the threshold, the relevant task is impossible. And we know that our computational threshold is conditioned on the low degree conjecture, and where we show the failure for low degree polynomials algorithms. Pictorially, the result in the previous slide could be summarized in the following diagrams, where we determine the red regions, meaning that it is statistically impossible to achieve detection or recovery. The yellow region, whereas we know that some algorithm potentially exponential, some potentially exponential time algorithm achieves the relevant task, but we condition on low degree conjecture. There is no polynomial time algorithm achieving succeeding in the relevant task. And the green region, the easy region, where we know a polynomial time algorithm succeeds for detection or recovery. We also give some further results in the extreme case for the planted total ordering. We show that the computational and statistical threshold are both given by Q being n to the minus 3/4, and the computational and statistical threshold is given by Q is equal to n to the minus 1/2. This result would avoid n to the little o1 factor and pins down the precise threshold in the planted total ordering situation. And as we also remarked that we also show that a natural spectral algorithm tries to distinguish using the top singular value of the skew symmetric agency matrix is suboptimal. We also gave the following result for the planted order click situation. While the results in log density setting apply here too, we show that the following stronger result for recovery. That is whenever k is omega squared root of n, exact recovery of the planted order click can be achieved by a polynomial time algorithm. So we start giving a brief introduction to the low degree polynomial method. So we will consider polynomials in the input skew symmetric 0 plus minus 1 matrix. And some examples of these polynomials include counting the number of directed edges of the input graph, or counting the number of subgraph homomorphisms for a small directed graph H, or approximating the top singular value singular vector with the power iteration algorithm. So why do we care about low degree polynomial algorithms? There are a few reasons. One could argue that they are often powerful enough to capture the best known polynomial time algorithm for statistical problems. And they also have nice algebraic structure that makes it possible to show failure of low degree polynomial method. And showing the failure of the low degree method are considered as evidence for average case hardness due to a low degree conjecture. So how do we show the failure of low degree polynomial algorithms? For the detection problem, it is enough to consider the following quantity called a low degree advantage or low degree likelihood ratio. And this quantity is defined as the supremum over all degree D polynomials of the ratio between the expectation under the planted model of f over the square root of the second moment of the f under the null model. It is known that whenever the degree D advantage is bounded, then degree D polynomials fail to distinguish P from Q. For the recovery problem, there is a similar quantity called the low degree minimum mean squared error, which is defined as the minimum mean squared error achieved by the best degree D polynomial estimator, showing a lower bound for the low degree MMSE rules out degree D polynomial estimator for the recovery task. One crucial tool in the analysis of low degree polynomial algorithms is an orthonormal basis for the knot distribution. And in our case, we have the following explicit orthonormal basis for the knot distribution, defined by over pairs of subsets of the edge set HAB, where HAB of G is defined as the product over edges in A with the appropriate normalization, and product over edges in B of the Gij squared minus P over square root of P times 1 minus P. And these polynomials form an orthonormal basis for the knot distribution under the inner product given by the expectation of f times G under the norm model. So using this set of orthonormal bases, we can rewrite the low degree advantage in the following way. So the degree D advantage can be written as the sum over all degree D basis elements HAB with degree D with degree at most D, and we sum over their first moment under the Ponton model squared. And further, we show that the expectation under the expectation of HAB under the Ponton model is 0 whenever whenever B is not empty, or if one of the connected components of A has an odd number of directed edges. And we give a quick proof of the second claim, that is, whenever A contains a connected component with an odd number of directed edges, this expectation will be 0. So first, we can split the expectation of G times A into a product over the connected components due to the independence between different connected components. So we can write it as expectation over G to the delta over the connected components. And then we can show that this is equal to the following quantity, where in the end we have this this expectation over uniform random permutations on this in the symmetric group of this -1 to the number of inversions. And we can show that this will be this will be 0 whenever the number of edges in the connected components is odd due to a symmetry argument. And thus, due to the previous observation, we could further simplify the low degree D advantage in the following way, so that we only sum over A with all components having even number of directed edges. And it turns out that for these kind of graphs, we always have the vertex set of A is the number of vertices in set A is at most 3/2 the number of edges in A. And we further use the following bound on the moment of GA under the Ponton model. We could show that the low degree advantage is equal to 1 plus log 1 for polylogarithmic degree, and when the parameters in log density setting are in the hot regime, that is when beta is at most 2 alpha over 3 plus gamma over 3 plus 1/2. For the recovery problem, we actually showed a low degree hardness for even recovering the support of the community S. Let X be the indicator vector of S. For X and G jointly drawn from the Ponton model, the low degree MMSE can be written in the following way, where we first use the symmetry over the coordinates so that we can split the sum split the expectation into a sum over each individual coordinates, and by symmetry, they are equal to the expectation for the first coordinate. So it's n times the following quantity, and the last quantity is we call it a low degree correlation. So that to show that low degree mean squared error is large, it is enough to show that the low degree correlation is small. So we will for directed graph G drawn from the plotted model, we will write G as the following product of matrices, where the circuit product are the entry-wise product. So P will be a matrix containing Bernoulli P entries. Z will be a uniform random skew symmetric Rademacher matrix. And X is, as defined earlier, will be the indicator vector of the community. And Y is a skew symmetric Rademacher matrix whose entries are more likely to align with the hidden permutation, with the latent permutation on the community S. Using the strategy of Jensen inequality trick applied by Spielman and Wein in their previous work, we average out the x and y variables and work with a null distribution that only involves the p and z variables in the denominator, so that we can further upper bound the low degree correlation by the following quantity. And omitting some details, and we refer the interested readers to our paper for the full details on how we can further upper bound the low degree correlation. And in the end, we can show that the low degree correlation is much smaller than is much smaller than expectation of x1 squared whenever k is below the square root of n over k times square root of p, which is exactly the hard regime in the log density setting. And when k is above this, we actually have a simple spectral algorithm to recover both the support of S, both the support of S and the latent ranking on S. So we will work with a Hermitian matrix I times G. Recall that G is skew symmetric, so that when we multiply the imaginary unit I to G, we get the Hermitian matrix. Suppose we fix S and the latent permutation pi on, and let us suppose the permutation is the identity permutation without loss of generality. Then we can decompose I times G into a deterministic part, the expectation of I times G, and the random part, which is I times G. And we know that the expectation of I times G has the following nice structure, which will be 2 times I times PQ times the following matrix, which has a non-zero block supported on the community S and zero everywhere else, and on the S by S block of this matrix, we get +1 in the upper diagonal and -1 in the lower diagonal. By Davis-Kahn theorem, if the spectral norm of the random part is much smaller than the spectral gap of the expectation of the deterministic matrix expectation of I times G, the top eigenspace of I times G will be very close to the top eigenspace of the expectation of I times G. And moreover, the top eigenspace of I times G not only encodes the support of S, but also it encodes the latent permutation pi of S. So below, this picture shows one eigenvector of the top, one eigenvector of the top eigenvalue of expectation of I times G, which will be and we write down its coordinate values v1 up to v of S, and for every coordinate not supported on S, we have its value in the eigenvector will be 0. So on the imaginary plane, the coordinates are evenly spread out on a semisphere in a counterclockwise order. So by explicitly computing the spectrum and eigenspaces of this deterministic matrix, we could show that a suitable rounding of the top eigenvector gives a good estimate of the community S and the latent ranking pi whenever k is above this computational threshold. Moreover, in the case of the pointed order clique, by an actual post-processing step similar to similar to the pointed clique situation, we can show that exact recovery can be achieved by a polynomial algorithm whenever k is at least some constant times square root of n. Finally, we also showed using the spectrum method does not work well for detection, and we consider the pointed total ordering setting where we have p equals 1 and k equals n. When G is drawn from the null model by standard random matrix theory, we know that the rescaled top eigenvalue of I times G converges to 2 in probability. And when G is drawn from the pointed distribution, again, we consider the same decomposition of I times G into a deterministic part and a random part. And this is similar to a low rank perturbation of a vector matrix, except that the deterministic part expectation of I times G is actually full rank, but it actually has a rapidly decaying spectrum, and this allows us to essentially treat it as a constant rank matrix. Using known results from random matrix theory, we can show that whenever Q, the correlation strength Q is at most pi over 4 times 1 over square root of n. And 1 over square root of n times the maximum eigenvalue of I times G will converge to 2 in probability, which is much worse than the computational threshold n times minus 3 over 4. In summary, we studied a natural random model of random directed graphs with community structure, and we pinned down its computational and statistical threshold. Thank you for listening to the talk.